Hello again. So I said that taking integrals is harder than taking derivatives, and that it's easy to write down integrals that we just cannot take analytically. And the reason for this is that there's no integral equivalent of the chain rule. There's no integral equivalent of the product rule. There's no integral equivalent of the quotient rule. So anything with multiplication, division, or composition is immediately going to turn into a huge problem. And there are a number of techniques that we learn that try to take integrals of functions like that. They're usually fairly specialized, like there's a technique that works for rational functions and only rational functions. We get into really specialized territory. Well, in an applied calculus class, we want to steer clear of the really specialized territory. So we'll present one, maybe two of the more generally useful techniques. And probably the most generally useful technique is called substitution. And even though I've said this is a pretty useful technique, it's still extremely specialized, at least in form. Substitution is for taking integrals of compositions. So integrals of f of g of x, but only when we also have the derivative of the inside function being multiplied by the composition. So substitution, suppose we have the composition the square root of x squared plus x plus 1 dx. This is a composition. The outside function is the square root. The inside function is x squared plus x plus 1. If we happen to have a 2x plus 1 in front of the square root, we'll be able to integrate this using substitution. We've got the composition and we've got the derivative of the inside function. So here, substitution works. By contrast, if we just had the square root of x squared plus x plus 1 without having the derivative in front, u substitution doesn't work. If we had the square root of x squared plus x plus 1, and we had x cubed in front, this substitution method doesn't work. We have something in front of the square root, but it's not the derivative of the inside function. So even though I called it kind of general, this is a pretty specialized technique. We need to have functions that look a very specific way if we're going to use U substitution. All right, but what is substitution? Or U substitution, as I just called it. The reason I called it U substitution is that to do it, we define a new variable U, which will be the inside function, and a new, not it's not a variable, I don't know what to call it, a new thing, du, which will be the derivative of u dx. Let's see how this works. I've said that substitution will allow us to tackle the integral of 2x plus 1 times the square root of x squared plus x plus 1. So let's do that. 2x plus 1 times the square root of x squared plus x plus 1 dx. And I've said that we should let u be the inside function of the composition. So we'll let u be x squared plus x plus 1, and we'll let du be 2x plus 1 dx. And what this is going to do, it's going to let us change our variable from x to u. Let me start just by moving things around a little. When you multiply, order doesn't matter. So I'm going to take the 2x plus 1 and I'm going to move it to the end. So we get the square root of x squared plus x plus 1 times 2x plus 1 dx. And maybe now we see what happens. We've got the square root of x squared plus x plus 1, which is this new variable u. So we've got the square root of u, and then 2x plus 1 dx is du. So we've got the square root of u du, and now we don't have a composition anymore. We just have the integral of a power function, which we take by bumping the power up by 1 and then dividing by the new power. The new power is 3/2. Division by 3/2 is the same as multiplication by 2/3. And we don't forget our constant of integration. And now we've got 2/3 u to the 3/2. But u is x squared plus x plus 1. So that's 2/3 times x squared plus x plus 1 to the 3/2 plus our constant of integration. And we have taken the integral successfully. And in order to take the integral successfully, everything had to turn to u. So our variable x had to turn into u, and also dx had to turn into du. And it's that last thing that causes u substitution not to work unless we have the derivative of the inside function out front. Like, say we tried this same trick with the square root of x squared plus x plus 1 by itself. I've already indicated it's not going to work. You let u be x squared plus x plus 1. You let du be 2x plus 1 dx. Well, this square root turns into the square root of u. No problem there. But it turns into the square root of u dx. How could we get a du? Well, to turn this dx into a du, in addition to having the dx, we need to have the 2x plus 1. And we just don't. It ain't there. So we cannot turn the dx into du. And we have to stop. And you know, it's the same thing here. I gave another example where u substitution doesn't work. If we had an x cubed, and we try to take the integral of x cubed times the square root of x squared plus x plus 1. Now, if we try to let u be this inside function, and du be 2x plus 1 dx, we run into exactly the same issue where we can turn the square root into the square root of u, no problem there. But then we need to turn the dx into the du. And to turn the dx into the du, well, we need the dx. Okay, good news, I guess. We have that. But then we need 2x plus 1. And again, that's just not what we have. We have an x cubed. No good. Have to stop. So this is a pretty delicate method. It's redeemed by the fact that we can use it when we're missing constants. constraints, or when we have constants that we don't want. We can deal with constants, and it's then further redeemed by the fact that, a lot of really important examples turn out to be just little u substitutions. And we'll see what I mean when we deal with missing or extraneous constants in the next video.